Good morning, everyone. Today we are going to be doing lecture 4. It is a long lecture, so be prepared. We got a lot to cover. If I'm going fast, please press pause and get the notes down that you need to get. Okay. Well, let's get going. Okay, so box E. Describe unlimited growth of the bunny population when resources were unlimited. Okay, that means that there was no starvation and there was no predators. What did you notice happening to the predator or to the population? Okay. So this is what the graph looked like. This is on your doodle sheet. So without any starvation or without any predation, right, meaning predators to eat it, the population will continuously go up. Okay. So if you didn't write that down, take a second and put that in your own words in box E. This is called exponential growth. This is a key term. Exponential growth is the growth rate of a population that increases faster as the population grows. This occurs when resources are unlimited. In most scenarios, resources are rarely unlimited, so this is very rare. Okay, exponential growth. Exponential growth means that first we start with 2, and then we have 4, and then 8, and 16, and 32. So basically, the breeding pairs keep breeding and making the population just keep growing, right? Box F, describing the growth of the bunny population when resources were limited. Okay, so what happens when there only was a certain amount of food, and when there was there's not predators on this one. Sorry. So now there's limited food. Okay, that means resources are not unlimited. Okay, so what did you notice happening? Please write that down in box F. So this is an example from nature. So here we have the breeding male fur seals in the thousands, okay, and the time over years. So in the early 1900s, we see that the population was really low. There was about 1,000 of them. And these are the males that are able to breed, it sounds like. And as time went on, the population exponentially increased, but eventually it looks like it capped off. Okay, so what is the reason for this cap off, right? What is the pattern in this graph? Okay, here's another one. Okay, the number of sheep. We have exponential growth for a period of time, and then it stabilizes. This is called a carrying capacity. Okay, carrying capacity is the maximum population size that an environment can support. There's only so much food, only so much land. Okay, this is the carrying capacity. And so this is like the stereotypical growth of a carrying capacity. So it goes up exponentially for a time and then it levels off. So carrying capacity moderates the growth of populations by slowing, stopping, or increasing growth that is dependent upon limited resources or conditions. So if the food source of a deer population can only support 1,000 deer, that is the carrying capacity for that population. As the population of deer increases, the food source decreases and competition occurs. The deer that are better adapted to obtain the food source will survive, while others will die off. Box G, fill in the blanks. Limited resources prevent populations from growing exponentially. That's what does the natural selection activity teach us about populations. So that was the FET that we did earlier this last week. This is also partially because of limiting factors. Factors within the environment that limit the population size or the carrying capacity. Key term, make sure you get this down. So limiting factors are the availability of living and non-living resources. It can be predation, it could be disease, it could be competition, right? Competing for food resources. Will the carrying capacity stay the same forever? right? Well, the current limitations on a population, so for example, the human population, right? We can only grow so much food. We can only chop down so many trees, right? We don't have any predators, so we don't have to worry about that. But will the carrying capacity stay the same forever? Okay, so just to tell you a little bit more about this, the limiting factors will change. We might get more resources, or we might be dealing with less resources. But at the rate that specifically the human population are using resources, something's going to change, and it's not going to be for the better at the rate we're going. Okay, box H, 2 lessons from the natural. Whoop. Okay, 2 lessons from the natural selection activity. There is a constant struggle to survive, and 2, survival and reproduction are necessary for change. That was weird. It wasn't showing the box H, and then when I moved it, it popped up then. Okay. Make sure you get those down. Okay, so now we need to update our model. Okay, in your model, you also said that there were different beak sizes in the finch population. Okay, so different beak sizes in the finch population. You don't have to write anything down right now. Just keep things in mind, because we're going to talk about this either today or tomorrow in class, depending on today, or if you're doing this tomorrow, yesterday in class. Okay, so we have some examples of variation. So we have different ladybugs, different birds. I'm going through these quickly, but you can, just at a glance, you can see huge amounts of variation in these species. Okay, look at frogs, dogs. Oh, look, they're so cute. Kittens, puppies, tomatoes. So box J, is variation the norm? What do you think? Yes, no, maybe so. Hopefully you write down yes. Okay. So the percent of, looking at this graph is talking about birth weight in infants. Okay. So here we have the percent of births in a population, the birth weight, and percent of infant mortality. Okay, so what I'm seeing here is that babies that are born with a 6 to 8 pound ratio have very low infant mortality. That means that they're more likely to live. Okay, fish length, we see this bell curve that we talked about once before. The height of people in inches, once again, there's always this bell curve. There's this increase of people towards the median or the average, and then a decrease as you go out. So box J, is there a consistent pattern? Describe it. What's the pattern? What is that word I used a couple of times when looking at this? Okay. Box K. So you guys did this. Okay. Which bunnies were dying when the food was tough like this? Okay. Was it the bunnies with the short tooth or the long tooth? What do you think? In box L, which bunnies were living? So when the food was tough, what bunnies were living? What bunnies were dying? When wolves were present in the warm climate, when wolves were present in the cold. What did you guys notice? Fill in those questions. Okay, when the wolves were present and it was warm, what bunnies lived, what bunnies didn't? Hint, I would look at the color. And finally, when the wolves were present in the Arctic, which bunnies do you think had an easier time, the white bunnies or the brown bunnies? Okay, write those down. Okay, so another example of an advantageous and disadvantageous trait. Okay, so in the summer months, which of these would have an easier time blending in? Okay, probably this one. You could probably blend in with the trees, right? But in the winter months when it was snowing, who do you think might be better suited? So this guy. So I think that it would be advantageous in certain seasons to be this guy, but not advantageous during other seasons, right? As we saw in the bunny trait. So an advantageous trait. So an advantageous trait is a trait that helps an individual survive in a given environment. Key term, please write that down. A disadvantageous trait is a trait that is unsuitable for the environment and may lead to death in the struggle to survive. So what will happen if an individual with an advantageous trait gets to reproduce? Okay, what will the offspring look like? If more individuals with advantageous traits survive and reproduce, what do you predict will happen to the number of individuals born with the advantageous trait in the population? Well, it should increase, right? What about the number of individuals with the disadvantageous trait? Well, those should decrease. Okay, so let's review what we've done so far. So we observed the phenomenon that traits change over time and wondered how this happens. We turned to the finches to seek evidence that may help us answer our question. Based on our evidence, we developed a model to explain the trait change over time. And we investigated our ideas further, revising our model. Okay. So this is what we get. So writing a model-based explanation. So using your model and other information you gathered during the investigation, you'll write a story of the peppered moth, so a full explanation, basically an answer to our question. First, you'll write your answer individually. On your model-based, okay. So for box N, what you're going to do is you're basically going to fill in the blanks on this moth story. Okay, using your model and what we know about the moth. So ignore this first, write your answer individually in your model-based worksheet. Don't worry about that. You're filling in box N. Sorry, that slipped through from the normal lecture, but we adjusted it to fit the distance learning, and that just slipped in. So please ignore that. It's gone now. You won't even be able to see it on yours. Okay, so we're going to be talking about moths. So we already talked about moths a little bit. Okay, so this is our model. Okay, I suggest you have this open while you work on this. Okay, so the moth story. So I'm going to tell you a little bit about the moths, and you're going to use the model to complete box N. Okay, so the Industrial Revolution created pollution that darkened the trees. So previously the trees had kind of a speckled pattern, right? There was dark spots and light spots, and the moths were speckled. So they blended in. Okay, after the Industrial Revolution created the pollution, the smog or smoke made the trees have more of a darkened color because of all the coal. Okay. Because of that, the speckled moths became less common and the black moths became more common because they can blend in on the tree. Okay, so you are going to use keywords from this model to fill in box N. Okay, so now we are now going to investigate how our model and our explanation compares to other models that have been proposed to explain trait change over time. But first, a brief history lesson. So follow along and fill in box O of your doodle sheet. So 400 BC, the Earth was 7,000 years old. Species were created separately and organized into an unchanging hierarchy with humans positioned just below ancients. So this is what they thought at the time. Okay. In the 1700s, they thought that evidence emerged that proved that the Earth was over 7,000 years old, that life had changed over time, and many species had become extinct. Organisms, though different, share many characteristics and seem to have a common ancestor. And in the 1800s, if life had changed when a question emerged, why do traits change over time? And several models were proposed. Okay, the first model was presented by Charles Darwin. So Charles Darwin thought that more individuals are born in a species than the environment can support, and there is a struggle to survive. Within every episode, there is a naturally existing variation. Variation of some give them an advantage over others in the struggle to survive. More of these individuals will survive and reproduce than those with less favorable traits. Many traits are passed from parents to offspring, and more individuals with favorable traits reproduce, so the number of individuals with favorable traits increases in each generation. The number with less favorable traits decrease. Eventually, the favorable trait becomes the most common form, but variation still exists. Okay, so this is actually box N. So you're going to fill in the blanks here for box N. Just going to delete that. Okay, sorry guys, it looks like it's a little out of order and I'm so sorry for the confusion. Unfortunately, I don't have time to start this entire lecture over, so please bear with me. I'm going to be adjusting some slides as we go to make it easier for you guys to understand, and I'm really sorry about the confusion. I did not develop this lecture. Another teacher did, and I should have double checked it before I started lecturing this bit, and I apologize for the confusion. But we got to keep going, and I don't have time to start this whole video over a couple of slides, okay? So please forgive me. Just hang tight, and we will get through it. Okay, so that was box O. Okay, so I'm sorry. Box N. Okay, so all of these highlighted words need to get written down into box N. Okay. Okay, so based on his model, let's see how Darwin explained a specific phenomenon. So how did giraffes with long necks evolve from ancestors with shorter necks? Well, many early giraffes have short necks, but there were some giraffes who had longer necks. As the giraffe population increased, there wasn't enough food within reach for all the giraffes. So the giraffes with longer necks had an advantage over the giraffes with shorter necks because they could reach higher. The giraffes with longer necks survived and passed on their long neck genes to their offspring, and the giraffes with shorter necks died and did not pass on their genes. Eventually, the giraffes with long necks became the most common. How does it compare to your model and explanation? Okay. So look at box N and compare. And look at the example. Did you notice any differences? Did you notice any? Yeah, I'm just going to delete that slide. Like I said, I'm sorry. I'm going to be adjusting this as we go because I want it to make sense to you guys, and I don't have time to start over. Okay, next, key term, natural selection. So natural selection is the process whereby individuals are better suited to their environment, survive, and reproduce more successfully than those less suited. Key term, make sure you get that down. Evolution, genetic change in a species over time, meaning many generations. And last key term in this set, adaptation, a change in the genetic makeup of a population that will allow a species to better survive and reproduce in a given environment. I can read, I swear, guys. Okay, so next we are going to be talking about the 4 types of evolution. Okay. We already covered this. You guys already did this part. Yes. So this was box O lecture that we did in class. The link was on the agenda. If you need to look at it, please go to the previous agendas so that way you can get all the information you need. And we are starting here. So we are now at doodle sheet part 2, covering speciation. Okay, so species, insert key term, a group of populations whose individuals can interbreed and produce viable offspring. Speciation, formation of a new species from a pre-existing population. So, for example, we have a pre-existing species, and over time, these members of this species slowly adapt to form different populations. Box A, requirements for speciation. So this all needs to get written down. I know it's a lot, but you can do it. So speciation can happen when populations become isolated, the geographic isolation or reproductive isolation, and isolated populations evolve independently. So mutations, DNA molecules change, leading to different traits, and natural selection. So mutated traits are selected for or against. So either the mutated traits are good or they're not. If they're good, they'll continue on. If they're bad, unfortunately, that species is likely to die, or that animal that has that negative trait is likely to die. And time. Over many generations, the traits that work the best in the environment will be passed on. So next is key term, geographic isolation. Okay, that's scooched down. It's going to be right on towards the bottom of this doodle sheet table. Okay, so an example of geographic isolation. So for example, the Grand Canyon squirrels. So each species of squirrel will adapt to its own environment and over time become genetically different. So these squirrels were once the same species. However, one now lives on this side of the Grand Canyon and one now lives on this side of the Grand Canyon. So they adapted to better suit their slightly different environments. Okay. So why does geographic isolation cause speciation? An organism may fill a different niche in the ecosystem, and different predators may also be present. There might also be different food sources. Okay, so for example, if this was the grassland and all of a sudden a river started flowing through, these guys are now different, right? There's different food sources, and that's it. Reproductive isolation, obstacles to mating or fertilization between population groups in the same area. So let's say that one group has these different set of traits. Well, one of those traits that they can inherit is the ability to no longer mate with the former members of their species. So therefore, they would be creating a new species who could only reproduce with each other, because that's kind of how it goes. Species should only be able to mate with each other. So box B, examples of reproductive isolation. So different habitats, different mating times, different mating calls, anatomically incapable, right? So one lives in the trees, one lives in the ground. They're not going to be able to mate then. Their mating calls are now no longer compatible. And then time. Snowdrops are flowering in the spring, in the winter. They're not going to be able to mate with anything that, or crossbreed with anything that's flowering in the spring. Okay. And that is all I got for you guys. I am so sorry that this was a little confusing. Please forgive me. I am going to go back and put notes on the slides to help you understand some of the changes I made during this video. But I hope you guys have a good day. And once again, I'm really sorry for the confusion, but I will see you I'll see you when I see you, because you might be in group A, you might be in group B.